What's up everybody, Haynes Curtis here. Today, I'm going to reveal to you the 20-ton monster that moved into our lab this summer. So for those of you who don't already know, I'm a master's student here at the University of Georgia, working under the direction of Dr. Ben Davis in the Dynamic Devices and Solutions Lab. And after 2 years of development and design, we finally got our high-speed water tunnel installed in our lab this summer. And, well, for us, that's kind of a big deal. What is a water tunnel? Well, I'm glad you asked, because this video is going to be all about water tunnels, what they do, and what's particularly special about our water tunnel. A water tunnel is an experimental apparatus used for testing the hydrodynamic behavior of submerged bodies in flowing water. Yeah, most water tunnels work off of the same operation principles, whether they're low speed or high speed. First of all, they're driven by a pump which recirculates water within the water tunnel in a closed loop. Second of all, turning vanes are used at each corner to make sure that the water is able to navigate smoothly through each of the corners. A honeycomb structure of some sort is used to straighten and smooth out the flow before it enters the contraction, where the water is accelerated to its final testing velocity, and it also squishes out the remaining turbulence. Some of you might have grown up watching the show Mythbusters, which I definitely did. And if you have, you probably are familiar with the experiments that they ran in the NASA Ames water tunnel. Now, the NASA Ames water tunnel is what is known as a low-speed water tunnel, operating at or below 3 meters per second. And this is pretty representative of most of the water tunnels available in the US. These low-speed water tunnels are used to mainly study what is known as flow visualization, where they inject dye or hydrogen bubbles into the water in order to see how the flow will go around a particular test article. Our water tunnel is a little bit different. It's what is known as a high-speed water tunnel, and ours can approach speeds a little bit over 10 meters per second. We can run flow visualization studies in our tunnel, but ours is primarily used for what is known as fluid structure interaction. In other words, we're looking to see how structures vibrate in response to the fluid flowing around them. Our water tunnel is a little bit unique because it has a test section that is a foot squared. The reason that this is unique is because most water tunnels that run at or above 10 meters a second usually have a test section of about half a square foot or smaller. Our tunnel was built at the University Instrument Shop, where it took nearly a year and a half to fully construct. And it's made out of almost exclusively 304 stainless steel, which is not exactly cheap. The tunnel is driven by a 125 horsepower electric motor, which has gotten us up to about 11.3 meters a second before we got cavitation, and we still had plenty of horsepower left. Just to put that in perspective, at 10 meters a second, we are sending water essentially from one end of the lab to the other, which is about 35 feet in under 1 second. Yeah, that's pretty cool. Now, if that's not enough for you, it's also putting 275 gallons per second through the test section. Think about that. Your bathtub is maybe like 100 gallons. It's doing twice that, if not 3 times that, in what, like less than a second. Does that not just blow your mind?
Wow. Wow. Wow.
As an undergraduate, I was very fortunate to be a part of this project, and I helped design some of the critical components of the water tunnel. But the guy that we really have to thank for making this whole project possible is Fortner, who runs the instrument shop down at the end of South Millage. There are probably a couple things that are pretty obvious in terms of what we're going to test in our water tunnel. That includes models of boats, submarines, torpedoes, propellers, other things that operate in water. What might not be quite as obvious is that we can actually stick models of aircraft in our water tunnel as well. And as long as we keep the Reynolds numbers about the same as they would be in air, our experimental results are just as valid as if the test had been done in air. So now that you have an idea of what we can study in our water tunnel, you're probably still asking yourself, why does this matter? Why is this significant? Why study fluid structure interaction? Well, like many other areas of engineering, and in particular engineering research, we're studying failure. We want to find out, why did this explode? Or why did this break? Or why did that aircraft fall apart? By studying fluid structure interaction, we can prevent bridge collapses, we can make sure that our aircraft are safe, and we can do things such as make sure that our nuclear power plants are not going to have a complete and total meltdown. No! Now, on the bright side, we're also not just studying fluid structure interaction to avoid failure. We can also learn things by looking at models of fish, eels, other aquatic critters, and even airborne critters. Now, more interestingly, we can also potentially harvest energy from the vibrations caused in fluid structure interaction. Alright everybody, that wraps up this video, and I hope you've learned something informative and useful both about water tunnels and fluid structure interaction. If you like this video, make sure to subscribe below because I will be making more videos like this in the future, of course involving our lovely new water tunnel. If you like this video, make sure to like it. If you disliked it, make sure to smash that dislike button, in the famous words of Peter McKinnon. And this is Haynes Curtis signing off until the next video, and I hope to see you guys again soon.